Welcome viewers to the 21st episode of BeyondPhrenology, and we are delighted to have with us today Dr. Luiz Pessoa. Uh, Professor Luiz is a full professor of neuroscience at the University of Maryland, and he has been a practicing neuroscientist for about 3 decades now, considering his education in neuroscience as well. He started with his PhD in computational neuroscience, and thereafter he was a faculty in Brazil. He was more on the computation side of things, theoretical modeling and computational modeling. And thereafter, he switched to being an experimentalist, first at the NIMH, I guess at Bethesda, the
Yeah, in
NIH
Bethesda, yeah.
campus, right?
Yeah.
And thereafter at the University of Maryland. Since then, he has been running a very prolific and extremely productive lab, where fMRI is the main technology which Professor Luiz relies on to understand and probe how the brain functions. So welcome, Professor Luiz, to the show.
Thank you so much. Thank you.
So Dr. Luiz, you said that you did your PhD in computational neuroscience, and computational neuroscience comes in many facets. So what exactly is the role of computation in neuroscience?
Oh, you mean in general or in my education
Yeah,
or in...
your education, like your motivation to start with computational neuroscience, and in general, and where do we stand?
Oh,
Because
in general.
a lot of, your book, The Entangled Brain, which came out last year with MIT Press, a really important read for budding neuroscientists, also touches upon a lot of issues about computational neuroscience, or at least from the limitation standpoint. So,
Yeah, so just very briefly, I started with computational neuroscience because that was probably the only way that I could start, because I was never really in high school. We had towards the end of high school in Brazil, we used to choose one of 3 tracks that prepare you to go to college. And college in Brazil is very strange in the sense that after you finish high school, you choose your major. And then the entrance exams, you compete with people who choose the same major. So the last year of high school, I chose the engineering math side, and in that focus you study a lot, very little biology or other things.
yeah,
And there's a biology side that prepares you to go to medicine and other kinds of things in biology, and then there's a humanities side. And so I went to graduate, I went to college, I should say, and I did math and computer science, and that's what I thought I loved, and I did enjoy it immensely, and really loved it. But towards the end of my PhD, sorry, I can get into the dates completely wrong,
yeah,
but towards the end of my undergraduate degree,
yeah,
as lots of people have experienced something similar, actually. There were these books hanging around faculty
very
in
similar.
computer
Yes,
science, the PDP books, parallel distributed processing books, talking about distributed processing and how that might be model of the brain of the mind and brain mind and so on. And so, I was already really into research when I was an undergraduate. I was doing an honors thesis. I was starting to think about an honors thesis, and then I sat in my advisor's in her office, my mentor's office, and she had come back from some big conferences in the US, and she had the brand new books. And I said, "Can I borrow those books?"
yeah,
So that was it. That was it. I was hooked in trying to apply computational methods, formal methods, to understanding, presumably understanding, and we can talk about that a bit
yeah,
later, presumably understanding the brain. And
right.
then I did, yeah, I did some master's degree that you do in Brazil before pursuing a PhD. That's sort of like a sort of a required step in the Brazilian system of education. And then I came to the US, to Boston University, to do a PhD in what they called, because the department closed, cognitive and neural systems. But it's basically computational neuroscience, the school of thought that Steve Grossberg had been developing. There was a department that he and his wife, Gail Carpenter, headed, and that was the department that I did my PhD in computational neuroscience. So the role of computational modeling in neuroscience, I think my view is that it's extremely important, and we can expand on that, the strengths and weaknesses.
Yeah.
But let me just more chronologically mention that after finishing my PhD, I felt, especially after 1 or 2 years back in Brazil, continuing in that line of research, I felt that I was too detached from data, in a sense that I was basically doing model fitting. So I had some types of general architectures that I would favor because of my education. So adaptive resonance theory, or some kind of feedback, or some kind of contrast normalization, or some kind of architecture of some sort, and I would apply it to a phenomenon, to some data. And it started feeling more of as at the time, this is the mid-90s, so it's a very long time ago. For me, it felt more like an exercise in data fitting, sophisticated data fitting, and in a way that I felt too far from the data. So I said, I would like to get closer to the data, because I've been an avid reader and consumer of data
Right.
for quite some time now as a student, right? And so I felt that I wanted to immerse myself in that process, the experimental process of thinking of experiments that can study the processes and the mechanisms that we were trying to model, but more from an empirical standpoint. And then in searching for labs, I had colleagues in Brazil that had a lot of links, and colleagues here in the US, National Institute of Mental Health, Bob Desimone, Leslie Ungerleider, and many others across the country, because they themselves had done their PhDs in the US and continued to do their collaborations, to do collaborative work. So one thing led to the other, and Leslie Ungerleider her lab was very welcoming, and yeah, so she said, yeah, sure, come. We have a position here, have some funds, and yeah, I couldn't believe it. So I packed my bags and came to the US, and the technique that they were using there, Leslie was obviously known as an anatomist, but she was incredibly strong in experimental design and experiments, and she was doing fMRI at the time. So her program had a little bit of anatomy still, but it was mostly functional MRI and a little bit of lesion work in monkeys in collaboration with Bob Desimone. It was sort of like an extended lab. At the time, they were a couple, they were married. And yeah, so that was really a fantastic, really welcoming, incredible environment. It was one of these dream environments that somehow I just was really lucky to land into, and I just felt like someone in a candy store, a kid in a candy store, because all the projects people were doing, and not only that, the lab was an extended lab that had Jim Haxby was also one of the lab had 3 PIs. Jim Haxby was another PI, and Alex Martin was another PI. So these are really amazing people, and yeah, it was quite unique. And then Peter Bendettini then joined the group more broadly to support the imaging initiative at the on the NIH campus, new machines, new pulse sequences.
Yeah.
It was a very extremely exciting time that I was just
kind of a booming
lucky.
environment.
Yeah, I was extremely lucky. Yeah. So, but let's follow up. You had a question about what are the possible roles of
so computational neuroscience has also morphed over time, right? It has its roots in the old cybernetic theory, right?
Right.
Thereafter it adapted, as you said, like parallel processing and different. It kept absorbing different concepts from how parallelly the computation technology grew, right? And things
Yeah,
have
yeah.
changed since, and we apply computation, biology. I understand that, both at the level of, for instance, we have to model an ion channel, and we are trying to computationally model the ion channel dynamics. But then you have these larger models of how the overall brain functions or how cognitive system operates. So how do you think it has changed over time, and what exactly it has contributed to? Like, uh, can we think of neuroscience without computational neuroscience at that cognitive level?
Well, forgetting for just a second the past, and we can delve into the past and see what was successful or not. And I've been more of an experimentalist for too long to be the ideal person to discuss that. But I would suggest that moving forward, so here's my take, I think. My take is that moving forward, we really need to embrace it very strongly for the following reason. Perhaps for the first time, we are starting to have techniques that really can give data that are spatial temporally rich enough that without models or tools, physics, math, advanced statistics, what have you, without other tools, technical, typically from these other fields, it's not even clear what we can do with data anymore. Because, for instance, let's say when I started fMRI 20 plus years ago, the experiments were very experimental psychology type. So they have trial types A, B, and C, and then maybe you have a 2x3 design or 2x2 design, and so you could get the responses for 4 conditions and run an ANOVA, a 2x2 ANOVA, and then you get a main effect of emotion, a main effect of cognition. You get an interaction between the two, and so on. But the experiments that many of us are doing now are considerably more complex, not only in fMRI, but especially more so in systems neuroscience, so that they have many facets of dynamics and they have interactions between regions. You might have multi-regions. So it becomes unclear even how to analyze the data with the tools, the typical tools that we've been using, simply because we went from a situation in which we can have a lot of tools that were more on the univariate side of analysis, analysis portfolios, so to speak, to having to think about spatial temporal dynamics and multivariate patterns across multiple regions and their interactions and directed interactions, indirect interactions. So my take is that thinking of computational neuroscience very broadly in terms of a set of techniques that assist you to address the data, attack the data in ways that it can study it more deeply. So does that make sense? I don't know if that.
So here, are you talking about like using computation as a assistant tools? For instance, a lot of computation you cannot do manually, or you cannot do like simple softwares. So you have more extensive algorithms to do it. Is that what you're referring to, computational tools, or you're talking about the computational architecture?
No. I mean, no. I mean, for instance, so the idea is that the types of ways that we have to now to analyze data transcend the basic ways that we used to. So for instance, let's say you have hundreds of cells that you collect simultaneously, perhaps thousands, tens of thousands of cells that you collect simultaneously across time and multiple conditions, multiple regions. So you are only going to be able to advance your understanding of the brain processes that you are interested in if you have computational tools that you can actually make sense of those data.
No, I understand that idea, but
okay.
But what I'm trying to understand is, are you referring to computational tools in terms of the algorithms or in terms of the data processing techniques? Or are you referring to the computational the assumption that the architecture, of those, how those neurons are interacting and how they are actually, forming or contributing to cognition or a perceiving acting organism, there's a computational basis to that. So are you
No,
talking about those computation?
I'm
Yeah,
just referring to a technique of addressing complex data and not making any semantic or any
yeah,
connection to the fact that because we know the brain computes this way, we're going to have a computational model,
yeah.
that
Exactly.
parallel,
Yeah.
so
That's what I wanted to ask.
that's not what I'm saying. Obviously, there is that class of approach
Yeah.
that may or may not be successful in some cases, and it's more successful in some cases than others. But I mean, I view the need to embrace computational and tech and math, basically mathematical, computational, statistical advanced methods of data analysis to uncover the types of dynamics, transformations, and irrespective of what you might be assuming that the brain is
Right.
implementing some kind of specific computation, minimizing some functional or some form to minimize surprise or to maximize surprise or to do whatever to so it's sort of separate from that.
Okay. Okay. I see. I see. So it doesn't go into the etiology of how the brain functions in terms of computation. It's more at the level of analysis.
Yeah,
I,
that's the one that's that I mean I find that the one I started with that because I think that that's the uncontroversial one that we all need.
yeah.
So essentially that's an invitation for neuroscience to take more seriously the need that we're going to study the brain. We have to have
That I agree
a
with you.
toolkit,
Yeah.
right? So there are other applications, the other, or I should say, angles or approaches in which you have a very set way of thinking that the brain computes in a certain way, and then
Yeah.
so I have a computational model that says that it's doing some free energy, something or other, or it's doing some
Right.
whatever orthogonal decomposition of some kind, or it's doing some kind of trajectory in state space in some latent state space
Yeah.
that goes along some manifold of some form or another. So that always all those things intersect. But what I was suggesting is a
Right. Okay.
broader thing
Broader. I
prior
agree with you.
to yeah prior
But
to
do you agree that neuroscience has been a little slow in the sense? So, for instance, we can talk about atmospheric science. And atmospheric science modeling is very computational in the sense of adapting computational mathematics and technology and physical language. But at the same time, it is also dealing with a very complex problem because you have billions and billions of parts interacting, and you don't even know what exactly constitute a part. Uh, and we have these dynamic models, and we have become really, really good over time in predicting the weather, right? Despite having complex interactions, the way you mentioned in your book about the brain, right?
right
And if you look at weather science, they have been using these extremely high intensive, high throughput multivariate techniques,
yeah
and time and scale interactions, called interactions across scales, more on the multifractal and more kind of spectral analysis side of things
Mhm.
for like 3 to 4 decades now, and it has actually given up good fruits. But generally speaking, neuroscience has been a little adamant, especially in the last 20 years. It has become more computationally intensive, but it has adapted compared to how many neuroscientists we have, how much we do. It has adapted very few new methods or very few new approaches.
Yeah, I agree. I agree that I mean, to be honest, it has been disappointing and surprising given that, so I have a PhD in computational neuroscience from the mid 90s, and we didn't know where things were going to go, but I would not have anticipated that it would have taken so long, and that it only took off because of something that is probably not my favorite way of thinking about things, modeling everything. Now every model is like some kind of uh, deep learning type of approach to see, or recursive neural RNN, or recursive neural network, that that one takes these very generic building blocks and forces them and uses them to study some patterns and of your data, and then you use that as a basis to study that system in a way that, I find very similar representations, or
Right.
whatever. Let's avoid the word representations, but you
Yeah,
find some very similar aspects of your model that seem to have parallels in the data, and that is an explanation of it and whatnot. So I think that unfortunately it hasn't blossomed in a more general way, and it has grown in a very particular way that I think is a little too constrained, or too, it's a part of the space of things that people could do, but to me, it's not the most exciting part, and it just became too dominant of the whole formal computational neuroscience. Every grant and paper
yeah,
proposes to use some deep neural network to see if it matches some property or other of how real cell responds, or how the voxels are responding. And I just find it a way that is not the kind of original way that I was trying to suggest
yeah,
that computational neuroscience could be important for advancing our understanding, given the really complex nature of the data that we now handle. Because
yeah,
20 years ago, we used to handle data that are more manageable, right? Single cell
right,
data, and then you kind of do a bunch of tests on individual neurons and
right.
some average response or what have you. And yeah,
And you use the right word. It's a complex data. It's not complicated data. So so the techniques
yeah,
tend to be
yeah,
complicated and not actually talking to that complexity per se. They give an
yeah, I
impression, but
agree.
right.
Yeah, I agree.
And
Yeah, I
you
agree.
touched this very nicely in the first third of your book, in the first three chapters.
Yeah. So, yeah, so my attempt was to invite the reader to consider this angle of complexity in a different way than, so I decided to do something a little risky, because I didn't want to have a book with a tutorial on, I don't know, dynamical systems, complexity theory, all sorts of concepts in the very beginning of the book, and then build it up,
Yeah,
and perhaps even build it up a little more technically. I wanted to propose, I wanted the reader to, by reading those chapters, feel the need
yeah,
for ways of understanding the brain that require looking at the relational interrelations of these parts as integral to the way the system functions, and not as just a set of isolated parts that do their individual bits in well-defined parts, in well-defined ways that you can isolate and decompose from the rest.
right,
So I wanted to build the case that we're studying these systems that are highly non-decomposable, and by decomposing them the way that we've been doing,
yeah,
we might be learning certain things, but I think we end up missing key components of this organization
yeah,
that are being neglected. And they might work relatively well in some artificial settings that we have animals in very constrained environments. They're in a cage and they can only respond in a single way, or they have only two choices. They poke
right,
their nose this way or that way. or the animal is threatened with something and has only one choice, which is you cannot run, you cannot hide, you cannot jump, you cannot do anything. So what does it do? It freezes in the cage
Right.
because it, so then it seems, if you study the system that way, then it seems that you are studying something that is highly dedicated and matches really well the behavior that you're seeing. And I think that that type of approach comes from sort of like a tradition in science that has been very successful in physics, which is you isolate things as much as possible, right? To study one of the forces
Right.
or to study one aspect of the forces, and you
Yeah.
so build some particle accelerator, or you have a chamber kilometers down the earth to see how much there's going to be some particle that is going to
Yeah.
hit there, and I don't know, whatever contraption that you said is
Right.
that you set is always in the spirit of isolation, right?
How many neutrinos are falling on the earth? Every square meter.
Exactly. Yeah, something like a neutrino
Yeah.
experiment and whatnot. So the isolation
Yeah.
experiment is really central to the success of that technique, those techniques that have been incredibly successful.
And it goes
But
back pretty far in time, like to the time of
oh yeah,
Skinner, right?
yeah, it goes back in time for forever, right? So for a very long time. And the contention is that from a lot from other sides of ecological psychology, ethological psychology, and many others, is that we really need the animal in the rich context for us to understand how it really behaves, right? So and to understand if someone like me is interested in the brain, and I happen to be inherently interested in the brain, because this fascination of how the brain supports these complex behaviors, we need to study these behaviors in actual ways that animals behave. And
Right.
so backtracking a little bit, the dream of this isolated chamber preparation, you put the monkey in a chair, and the monkey
Yeah.
cannot move. It can only move in very minimal ways. You have the mouse in very specific ways. Was the hope was that we were studying these elementary components of brain and mind that would generalize to arbitrary conditions. For instance, in physics, you study something in an isolated setting,
Right.
and it seems to behave, gravity behaves in ways that seem to be preserved no matter what's its context, right?
Right.
But it seems that brain and mind seem to adhere to very different principles, which is this complete radical context emergence, which is,
Yeah.
it's not that it's completely arbitrary, but it's highly context dependent in a very even in a temporal unfolding manner. So it's something that if you isolate in trials that are instantaneous snapshots of a certain behavior, I don't want to go far as you not learning anything, but it really limits what the kinds of things that we can learn.
Right.
I mean, it comes from our own challenges, right? We want to study someone in an MRI environment. We can't have the person running around with some kind of helmet that is the equivalent of an MRI yet. If you want to study the rodent brain, then you had to have all the cabling and all the kinds of things, and that could only fit in some really constrained environment. So I'm not blaming the way we did it per se, but I think that we were strongly limited by the available technology. And I think hand in hand, the way that we were thinking that the brain functions. And I think it's an empirical question. A lot of people still think that way, and they could be right that we could be learning certain things that generalize quite well to a broad set of environments or conditions and settings. So it's an empirical question after all. But the suspicion that many people have, and I have, is that that just doesn't, that will not turn out. But it's just basically the battle of optimists versus pessimists, and we're only going to know in the future, because so the goal of people on the goal of the optimists that continue doing what they're doing. The goal of the pessimists is to show, it takes a little more work, is to show that under other conditions, then you get other results. So you have to find ways to study thing under other conditions. And people were not studying it under other conditions because it's not because they were lazy, it's because it was extremely hard and we didn't even have the technology.
Right.
So
There's a saying,
yeah.
you know, that behind every pessimist is a disappointed optimist. So so
Yeah.
so you touched upon two very important points. I think very, very important points for the future of neuroscience. One is the idea of generalization or context, which brings to the whole ecological domain, that what you
Yeah.
study needs to be ecological. And there has been recent call for it, you know, like for instance, one of the most cited paper by John Krakauer, you know, neuroscience needs behavior, for instance. And there have been
Right.
others of similar kind, like psychology
Yeah.
needs something along the same lines. And the second
Yeah.
idea of non-decomposability, that you cannot decompose, you know, parts of the system and tell that this is what the system does, because it might do it. It might do it in quotes within that particular you know, setup or constraint or
Right.
a limited set of circumstances. So it has to. So that means that we do not need to just innovate on what we study. We also need to innovate on how we study, because the statistics which we have or the hypotheses we design right now are basically based on decomposition. We generally do not think we have very limited ability to frame questions and frame hypotheses which adhere to the idea of non-decomposability of the brain or the central nervous system in general.
Yeah. Yeah. I find it disappointing. I don't know sociologically or scientifically the reasons, but I guess it's just these how scientific fields evolve. But I find it disappointing how little we find of people trying to study things on the interaction end of things, the relational
Yes,
component of
the
things.
interaction dominant dynamics of the brain rather than component dependent dynamics of the brain.
Yeah. So
Right.
I find it a little puzzling because I'm not allowed to discuss, and I'm not going to discuss anything, but I'm a part of grant panels
Yeah.
that review grants, and the grants, over and over, they're on the components, right?
Yeah.
Component A does this, and a component B does this. Component C, which is really close by, does
Yeah.
something else. And I do think that this mainstream thinking, even though when you talk to people, they deny it. They say, no, we don't think of the brain as
You
this
are touching on
way.
exactly the same things I wanted to
Yeah,
ask you and be open about
yeah,
it. Even
yeah,
the people who say that, you know, it's everything together. I won't take names here. There are people who have made careers in
yeah.
the last 5 years. They've gathered more than 50,000 citations. I know many people like that. Just
Uh-huh.
talking about and writing reviews. Oh, that we need to look at the whole brain. And when you ask them, do you have any single publication where you have a method or you have a way to look at the whole brain, or you have approached? None.
Yeah.
But it has become like fashionable to get more mileage in terms of citations.
Well, I don't know if it's, yeah, that's a slightly different aspect, but what I
It's a
would
little
say,
cynical, yeah.
yeah. What I would say is that, you know, the vast amount of papers or grants going through the system, if you will,
Yeah,
in our attempts to sort of isolate this part of the thalamus here, this nucleus of the thalamus, the reunions is doing this in the
yeah,
context of fear extinction. And it just, these functional concepts, these computational concepts, these whatever concepts, even the ones that we might not like so much, algorithmic or whatever, these
yeah,
general concepts, they're always mapped to one place of a region, and I find it surprising. I maybe it's probably because of my background. I find it surprising why more people are not trying to look at how these interactions may be supporting the very thing that they seem to be super interested in. Like, suppose I'm really interested
Yeah.
in fear extinction or whatever concept, or reinforcement learning. It doesn't matter, memory of this kind, or
Yeah.
it's a little surprising to me that it's still to this day it's so part oriented, a little part
But
of the
what if I
brain
say, what
oriented.
if I counter you that you are right? You're touching on the right sociological points, but people like me, for instance, I'm completely about interaction dominant dynamics, right? And the kind of
Right.
methods I use are highly, they just look for interactions across times and scales. And
Yeah.
that motivated me to read your book to begin with, even though a lot of your work is not,
Yeah.
is sometimes also orthogonal to how I think. Uh, but from a young researcher's point of view, and you can call it a sociological construction or the way the hierarchy in science works, or in general the funding panel works,
Hmm.
there is so much of it. I mean, it's so hard for a young person to get funding, and when you have the most productive years of your life, right? You're a young faculty and you're full of the energy to do something and actually change the paradigm, right? And that's when you spend that 5 year basically writing grants. And and when you look at the lesson which you are taught to read to send grants, write it simple, make it component wise, design your hypothesis so that the reviewers can understand. Don't use any new words. Use only terminologies which you think the review panel might already know. So the guidelines themselves are compressing, limiting any ability to expand, to innovate, even though the grant has a whole innovation section which is scored.
Yeah.
But you're not allowed to innovate from that perspective, you
I
think?
I I agree. I can't speak for NSF or
Yeah.
Europe, but NIH, the whole outlook for NIH to me is one that is just too centered on too conservative a view of like you said, studying something that is uncontroversial because you need those grants at any point in your career, but especially in the first few years. And it really doesn't promote or even give space for alternative ways of thinking. And I think that panels are inherently, they develop some emergent dynamics that is extremely conservative, and they just bring up concerns. I'm concerned about this, concerned about that, concerned about that. And so the only reason that one strategy to minimize concern is when you anchor it on ongoing questions in some interesting angle, a clever angle, an important angle even, but without deviating too much
Yeah.
things. So there's very little room to deviate.
Or to fail. I mean, and unless you
Oh
unless
yeah, oh,
you're
to fail. Oh yeah, oh yeah.
and
They
unless
think
science
they're
is
oh
willing to fail, like the very nature of science is high willingness to fail.
it's let we can't even discuss that, because then we
Uh,
would never stop here, because we would just spend 5 hours just talking about that, because the fail component is they're trying to take the failure out of it, because the only mechanism at NIH that I understand is more open to the possibility of failure is the R21 grant mechanism. Then that I witness panels being more open to the possibility that things will fail, and that's not a disaster. The failure is part of the process, because the problems being addressed are more original, more, yeah. So it does feel different when people evaluate R21 grants they're smaller in number of years. They're smaller in the total amount that is awarded, may be insufficient for lots of things. So established labs or even younger researchers trying to establish their labs, they can have an R21, but they need a larger grant, an R01. And those are reviewed in an incredibly conservative way, in my view. They're just there's almost no room for something that is more original and more pushing the envelope. And
so a lot of so maybe that a lot of progress. I mean, so coming back to your book is like it has this feeling, like that you've worked so much in neuroscience and you've worked hard, and finally you come to a realization that a lot of things are not in place. A lot of things are ignored, and we need to do a lot of things. And the first three chapters are basically a primer to that need and primer to the limitations. And it seems to be that the sociological limitation is more the grant structure rather than actually people's ability or people's propensity to do things, because 5 years is enough time for person to become conservative and adapt to a system to succeed more in grant. So you're selecting for like more conservative kind of people to be running labs.
There's a selection. I agree.
Right.
There's a selection for that. Yeah. And the people who get successful, they found ways to work within that system that allows them to do a little bit that might be the parts that they're more excited about, but within the constraints of having having enough that is within that system. Yeah, for sure.
So where do you feel the future of the component dependent neuroscience goes? Because at some point, given the financial constraint, or we will realize that why exactly are we doing neuroscience? What exactly are we doing it for, right? Whether we are doing it for like really understanding from the basic perspective, or we are doing for something applied, and even for a lot of phenotypic application. So for instance, we want to understand Alzheimer or Parkinson's in its fullest, right? So for instance, I'm right now working on Parkinson's, and pardon my adversarial nature a little bit, I was looking at posture, and some of my studies are focused on posture. When I go back and look at the posture literature, we call in neuroscience extended standing as like a 30-second trial as extended standing. Okay, 30-second quiet stance, right? And when you look at all the literature is basically based on the idea that you stand for 30 seconds without doing anything. And that can somehow tell you about Parkinson's and, related disorders and things like that. When in real life, we are never still for 30 seconds, and we are standing for like minutes at a time, and sometimes hours if you are working in a hospitality industry, right?
Yeah, in many kinds of work, yeah.
And there's not even a single study on posture, which, for example, looks at posture for 15 minutes. So even when we want to go clinical or applied, and let's say we want to be conservative, even then the question comes in, are we doing enough? Or how long can we sustain this kind of rut the way we do in general? I mean, of course, not all neuroscience is bad. A lot of good neuroscience happens. You have done a lot. But overall, how long can we continue? Will public start questioning sometime, or people will start questioning like, what exactly are we doing? Where are we in our understanding of the brain?
Yeah.
Other than
that's a really important question. It's extremely difficult one, obviously. I tend to think, and I'm not sure this is the best way to think, but I tend to think I tend to separate a little bit. I tend to think that basic research is really important. So one can say, oh, we live in a world that we don't have the luxury of just giving large grants to people just to do out of curiosity things. And I understand the luxury of being able to participate in a system that gives you research money to do basic research. And I do understand that, given the overall society and societies that we live in. And so, but I do think that if you differentiate, if you separate to some extent basic research from more applied research, if you're willing to do that, I think that we do not have to measure the success of the basic side of the science in terms of a more applied practical, what are we accomplishing that has had a clear impact on people's lives? For instance, let's say antidepressants, uh, everything about mental health and illness, right? So anxiety medication, or not to mention Parkinson's, Alzheimer's, the whole range of things. So I do think, uh, my opinion is that basic research is inherently important in laying the ground for understanding and discoveries that later, hopefully, that's the hope, will intersect with more applied types of knowledge building. But I wouldn't evaluate the success of neuroscience from the lack of tangible results along the lines that you were discussing before. So for instance, what have we done? So let's say, I don't know, we just put a long list of things. What have we done for autism? What have we done for depression? What have we done for...
No, I am on your side. I mean, we have done a lot, but I was saying more in terms of like either we should be having a lot of clinical, or we should actually have a leaps and strides development in how we understand, you know. And what I find unsatisfactory and
Okay.
what kind of troubles me in general is the resistance to something new in neuroscience as a general idea about how the brain functions, which exactly you talk about.
Yeah.
So that's what I was talking about, the existential
Yeah.
vacuum, which
Yeah.
that limitation creates.
Yeah, no, I agree. I agree with you. So for instance,
Yeah.
I mean, just think about it. I mean, I go to these panels and you don't see a whole really diverse set of ideas. It's very, like we were saying before, it's a narrow subset of the space of activities that neuroscientists could, the frameworks and the theoretical underpinnings. It's very, yeah, we created a system that does not, it's not broad, it's not
Yeah.
diverse, it's not, you know.
So in my field, motor neuroscience, 90% of motor neuroscience, or maybe 99%, is basically moving a manipulendum in like 2 degrees, right? And unless you move something in in like a planar things, there are not many grants actually beyond this movement. But
Yeah, I mean,
yeah.
I completely recognize that. I, but you know, the strange thing, and I don't know how to reconcile this, and I don't know if this would be the time to discuss this, but I, I so for instance, here's the puzzle. NIH does not dictate what I should find as good science. They
Right,
don't
it does
even,
not. Yeah.
I go to that panel. I've been going for that panel on and off for 20 years for these panels.
Yeah.
And I've never got something that says, you know, this is what we are interested in. And I mean, or we
Right.
don't like when it's too applied, or we don't like when
And
it's
program
too...
officers also don't say that.
I've never, there's, so
Yeah.
in a sense, there's some kind of implicit dynamics there that we collectively somehow narrow our minds. Because, so for instance, so it's for me to decide. So if we all, let's just imagine just an alternative scenario. Suppose we put there all those 30 people,
Yeah.
and they're incredibly open-minded. So they could be super excited about a proposed ecological psychology study, and one, I don't know, one super applied type of study, one super basic thing. So the whole range, but that's not what in practice happens. And so somehow it generated a system that the applications themselves are have been selected to be in that really narrow space in which they can be more competitive. But it's interesting, a little bit like the brain, I think, without a top-down controller that is telling, that I want only kinds of applications of this kind. So it's kind
it's
of
an
like,
attractor. It's an attractor space, right?
it's like, yeah, it is like, I have never read anything that said, oh, if
Yeah.
it's too, it's not like,
That's what one of the program officers. He was very humble and very kind of revealing and supportive, and that's what he told me, that it's not in our control, and it's not about the NIH. I mean, when we say that NIH does this, and we get frustrated when grants rejected, it's not the NIH. It's actually the review panel, and it's a constrained
yeah.
mentality of the review panels rather than the NIH.
And the review panel
Yeah.
are the same colleagues that, after the panel,
Yeah.
just last week,
Yeah.
we went out and had a great dinner together, like this is us, this is our colleagues. So I think we have to become a little bit more comfortable blaming ourselves.
Yeah. So do you think the review panels have to be shaken up? I mean, too much from me, like a first year assistant professor. But do you think we need to shake up the review panels? Probably.
Well, even more odd, we
Yeah.
have, because for a few years now, society has been more, it's clear that we have to have diverse panels. We have to have, so 20 years ago, they wanted full professors in these panels.
Yeah.
And because of that, the way science was, it was more male dominated, more obviously white persons, high associate degree, or later associate position, or full professors. The panels are not like that anymore. They are very diverse, and the composition is 50-50.
So it's more the dynamics of the panel than actually the composition of the panel.
I think
Coming back to that's like
I'm
brain,
a little
right?
bit, I think a little bit surprised. I'm a little
Yeah.
surprised because they managed to change this composition substantially, and it has. There should be a study for them to show how different they are, and they really are different. They're much better now. They're much better now. Sometimes there's a little bit of a problem, like someone who is very green in this process. Sometimes it's very hard for them to. It's a little tricky, but nonetheless, so that's why they wanted more more people in the past with more experience.
Yeah.
But that's other biases come in too.
Yeah.
So, but overall, it's clearly superior.
So maybe it's a dynamics. Again, coming back to, like, we have to think of organizations and brain, any collective system more in terms of interactions rather than as components. And components are actually replaceable. Interactions are not. Yeah.
Somehow, the interactions are still being
this is
dominant.
Very interesting point.
Yeah, it's like, and depressing, because we would like to have some more openness to diverse proposals, different viewpoints, different frameworks that can, because it's an incredibly complicated and complex system to study. So being open to very diverse kinds of approaches should be something that we should embrace, because it's only, if only given humility, you have to be humble about the thing. And so maybe, I love this thing, but maybe I'm completely off, completely wrong. So let's assume
that the wider the search space,
if we open the search space, then maybe we just
and when you look at the search models, right? Even if you look at like optimal foraging, whether you agree with the optimal foraging model or not, or a Levy-Walk model, I mean, the idea is that if you have not found a lot in this space, you rather change your space drastically and randomly in some direction than actually digging the same place again, right? So even from the search optimization perspective, it's not a conservative strategy is not good for science in general.
Yeah.
So that brings me to the idea of representation. And I know that you do not endorse representation the way hardcore computational neuroscientists do. And representation has been a dominant idea of how we think and design hypotheses and understand the brain. It starts with the assumption that brain has representations for everything. What we see, what we observe, what we plan, everything is represented somewhere, like like an exact copy or something in a very correlational sense. By the way, we are coming up with a book very soon. It's very close to contract. The whole book is about non-representational ideas about the brain and alternative metaphors than the computation.
Oh, wow. That
So
looks fantastic. Yeah.
yeah. So, but it seems to be that there's only one metaphor in neuroscience, the dominant one, which is the computational metaphor, and representations inherently come with that computation, right? So
Yeah, right. Because you manipulate a representation,
right.
basically sort of like an input output, and yeah.
Right. So you basically operate over manipulations. You change manipulations.
Yeah.
You make representations interact. So what I understand that it has roots in early computation systems, but do we have a simple empirical proof that there are actually representations that exist? I mean, a correlation between a neural activity and behavior is not representation. It does not imply representation. So why are we hooked on the idea of representation so much in neuroscience? Where is it coming from?
I think it comes from two places, at least. One is the obvious one that you mentioned, which is the links with computer science and logic and forms of AI with production systems, expert systems from the 80s and a long tradition that was very parallel to cognitive science in the 70s and 80s with a very linguistic language of thought type of description of mental processing. So in a sense, I think that's one of the reasons, but let's just skip that one for now, or skip that one completely. But I do think that an alternative, so let's say, I think that I'm a little bit cynical about how science operates in the following sense. I think that science, a few times, once in a while, someone comes up with some ideas that are not necessarily really good, that are not necessarily super profound. Let me backtrack. Someone comes up with a good idea, but this idea, what is important about it is that it kind of hits a sweet spot of sort of complexity and advance and complexity. Let me give you an example. I'm all in favor of network analysis in the brain. I like it. It's useful. It has its obviously huge limitations, but think of it. What happened with network analysis? With network analysis, there's suddenly in the mid 2000s and early 2010 tens, that there were a lot of techniques that one could basically plug and play.
Right.
And okay, I'm going to do a network analysis and look at centrality this, efficiency that, modularity this, whatever, right? So it becomes, the idea is really powerful, and you could think of dynamic networks that reconfigure themselves and overlap and dissolve, and you could think of it in completely enormous range of ways that you can think of it. But that's way past the sweet spot of being more manageable, such that you can almost have something that you can plug in and run an analysis and get a result and kind of interpret. So you go to this range of this sweet spot of innovation or power, but at the same time simplicity that a large number of individuals can use, right? So if you had some very complex types of networks that were more like sets of differential equations that have interactions and interact with each other with time varying weights and whatnot, that would be so complex that three individuals in the world working together with some people in math that do advanced dynamical systems, only those three people would be able to do that, because it's just past any, it's just, it's,
Right.
it's just a degree of difficulty that only one or two gymnasts in the world can try that routine, and the others do the more basic stuff and they do it well. And so I think what happens is that with the representational type of language and thinking, it does hit a spot, because if you think about it, it's sort of something that lends itself to trying to understand input and output structures that are transformed. And so how this representation is manipulated and transformed as a progression of steps are applied to this in a chain of applications, right? From an input all the
Yeah.
way to an output.
Yeah.
So I view it as a kind of like a perfect sweet spot that, you can teach a psychology student, you can teach an engineering student that can do more formal kinds of things, but you can teach lots of people these views, and they can do quite a bit with it. And so I think it entrenches that view as well. So is the combination of all that we talked about before in terms of some lessons or baggage from computer science and logic and original cognitive science that was very logic oriented, and computer science, computer metaphor oriented. And then this facility, because I can actually study, this transformations and say, and have a language to describe them too. Because let's think of an alternative. Suppose an alternative is something that is much more like dynamic, so that you would
Yeah.
more naturally think in terms of dynamical systems, much more less modularized, right? So compartmentalized, it's less so. So it's not even clear what's the input and what's the output, and you can think
Yeah.
of the
It's
transformations, but the
you
transformations are time dependent, and
you have to get rid of the whole. You have to dismantle the whole thinking process from the beginning to the end, and not
yeah,
just
yeah,
the processing.
you dismantle the way that the engineer can think or the
Yeah.
psychologist can think. And so, like, okay, how do they even think now? Because okay, so there's not a transformation so that another region is actually reading these inputs in a strict sense, because they're actually heavily jointly transforming in space and time these signals because of really powerful feed forward and feedback connections and all sorts of other connections with other brain regions. So how do we even conceptualize that? So it becomes something that we have not found, and I don't know if we're going to find, but we have not found a sweet spot of being able to use these tools such that most of us were normal people, or not like, completely, they're the three people that can do that gymnastics routine in the world, or the math or the physics or whatever that we can do. So I think that we
So
keep on trying to find these sweet spots. And I think
so
there are a lot of people in excitement now for dynamics, and hopefully we'll find it. But you see already where it's going. One of them is like, okay, we go to attractors. It's just one type of dynamics, and it can't
yeah,
even work.
exactly.
Right? It
Exactly.
can't even work,
That's
because
what happens.
if I get to an attractor, I'm here now. I'm going to stop talking to you. As soon as I get to the attractor, I'll stop.
Like it becomes a heuristic, at some point, and then a rhetoric.
Yeah, it's like these
Yeah.
heuristics, right? So,
Yeah.
okay, I can use attractors now, and that is starting to become doable. So more and more people are using it, and I can use some tools for manifolds.
Yeah.
So perhaps we develop some tools for manifolds that are interesting enough that we can learn a good amount, but then we're going to have to kind of dumb it down. Sounds bad, but dumb it down a little bit so that it's more manageable for lots of people to use it. I mean, just think of look, I am a functional MRI investigator. Why was functional MRI exceedingly popular and productive? Because there were a group of individuals in the 90s that were amazingly gifted, and they distilled their knowledge into packages that allowed people to press buttons, more or less press buttons, and do complex analysis. So you use AFNI, you use SPM, you use FSL. And so they were able to create a set of tools that me, the average scientist, was able to utilize it. And so the field exploded. And so if we're going to use dynamics, for instance, let's say we say that, oh, we're super interested. It's like, let's use, more naturalistic settings. There are no trials. So we're going to have to use something that is more dynamic, some dynamical system tools. Does it go, what are the kinds of dynamics? Is a saddle point, an attractor, a repeller, what have you. So I don't know, maybe some group develops some tools that you can put in the data and you can kind of like converge into some of these things and describe that you find 3 states and the states have these kinds of dynamics. So
it makes a lot of sense. I mean, it talks to both the sociological aspects of things and science as like a community activity, that unless you cater and recruit people to your cause, right, why would the cause would move forward, right?
yeah, I do think exactly this. I mean, I'm a very strong believer of this way of thinking, because I mean, it's just biases my way of thinking, because I just see it happen over and over again. So for instance, one of the reasons these neural networks now, these deep neural networks, these different models, convolutional, what have you, are very popular is also because, I take a first year student from engineering, they can implement it. They get TensorFlow or whatever thing, and they implement it, and they have something to optimize the learning, and they just create a loss function, and it's just, you have to have this mini production line type of environment in science, I think, unfortunately.
And low barrier to entry as well.
And low what?
Low barrier to entry.
Yeah. So because it creates a low barrier to entry, because you have a production line. So you have a production line, and okay, so you just say you have 12 layers, and you have this connectivity, and then you have this type of unit, and you have, so if you don't have that, then it becomes niche. It's like only a small subset of individuals can really fine tune to literally create a new computational model, like some colleagues do that, right? So for instance, when I was doing my PhD, there are some general principles, but everyone was creating sort of like a different kind of computational model. So I didn't use that model, so the knowledge doesn't transfer as easily. I mean, it transfers, of course, because I know some modeling, and there's another kind of modeling, I can learn it, but it's not like, you just look at a table and say, okay, now use this learning algorithm in this case, so.
Right. Yeah. No. This whole network thing, right? I mean, the way the science percolates now, it's very different. So there was a time when 1 or 2 or 3 people used to move fields, during the time of Galileo, during the time of Copernicus, or like anyone, right? And they were also not funded by the NIH or any central authority, So they did not have to navigate that sociological constraints at that time. So, but now we can do science. Now more people are actually allowed to do science. I mean, it's a luxury that, right? Like no matter from what background you are, you can do science. There are enough number of journals. There are enough ideas. But you have to kind of play the game if you have to succeed in the sense, not to take that word literally. That's a very, very interesting. So how do you get away with, like, what do you use in place of representations? Like, how do you explain your findings to the audience, which is tuned to think in terms of representations and input-output processing?
Yeah, I think there are some fields in neuroscience and in some types of studies. Yeah, I'm just trying to think about it. I think that we don't have to, even if the work is somewhat representational, so to speak, like it's not like some complete dynamical system thing that evolves in some way, that even if the work is not within that kind of a framework that is a strong alternative to more traditional viewpoints, I also don't think that we need to describe it as always in terms of strong versions of representation. So for instance, I mean, to be honest, like some of the work is rather basic. So we're trying to understand things. Let me just give you an example. We try to understand things that are fairly simple. So the extent to which, when there are threats in the environment of the participant, and when there are rewards in that that environment, how do these two things trade off with each other? So for instance, when there are threats and rewards, does it increase arousal so that you enhance your attention and you detect things better, or you process things better? Or is there what other people call opponent interactions, in which having both would actually decrease because they compete? They would not sum. So they would be the one that would be following either the reward or the threat. So
Yeah.
more according to some kind of opponent interaction type of description of the system. So I still think that there's a lot of neuroscience that can be done that doesn't have to be so strongly tied to
Right. Interpretations.
strong versions that are more representational. I do think that becomes more complicated, obviously, when people are studying things that are more, perhaps more symbolic, like for instance, planning, and there's certain kinds of problem solving that they might have a stronger version of implicit representational thinking. Or I don't know, sometimes, I guess, I don't know if I'm right, actually, because you can study vision, and you can say you can study vision and say that's low level, low mid level, whatever, high level, and say that you represent faces and you represent semantic features and some kind of semantic space. But I don't know if we have always to, I don't know if one always implies the other. For instance, suppose we find some kind of semantic space type of, that signals in visual cortex and in anterior visual cortex, anterior temporal cortex, let's say, anterior temporal, respond in a way that we can organize it in terms of kind of some semantic space of some form that maybe, I don't know, typical things are like animate versus inanimate, whatever the semantic spaces are. I'm not a semantics person. But let's say that semantic space makes sense to semantics people, the people who studies the semantics of objects and things like that. In your view, is that already inherently representational? Because all what you're trying to do there, in one sense, can be describe the set of responses and their relationships such that they have a certain organization. So sometimes I view it as I'm trying to understand the organization of the signals or the responses. And in a sense, you can make a direct connection and say, okay, what you're trying to do is to find the representations and how they're organized. But representations also come in a whole range of types of representation from right. So
the idea that you operate on representations versus can you have representations of the world, right? So even the ecological psychologists agree that we can represent the world, but the mode of that representation is not representational. In the sense, metaphorically, we have representations. When we close our eyes, we can think about things beyond our body, right? So we do have some form of representations, but the brain does not work as a representational device. At some level we can form representations, but that comes out of the dynamics and not out of representational.
So that's exactly what I'm trying to get at. So is it something that, for instance, those signals reflect certain kinds of semantic features of the environment that you're embedded in, but it's not that it's creating an internal representation of the external world as an explicit goal of what my visual system is doing. It's just by my interacting with this system, by my interacting with the world in this systematic fashion, then I do create certain types of responses, or there seem to be some kind of structure to the organization by which these parts of the brain respond that follow some properties of the world, right? So, but that doesn't mean that I am representing a face in the sense of I'm reconstructing the facial features and their geometry and whatnot for purposes that are more explicitly representation. I don't know if that makes sense, but I do see the fact that this close embedding of an animal in its environment and their learning history and their interactions with the environment will be such that some responses in the brain will be highly reflective or tuned to properties of the world. I mean, that's my view. It's an antiquated view maybe, but it's my view. But I wouldn't necessarily call them representational, but I don't have a problem, too much of a problem if people use the word it represents. I'm a sort of like more neutral in that debate in that sense. I do find the representation problematic when we phrase things as our representation is constructed by sort of like creating a model of the world inside our head as an explicit goal in situations that might not necessitate it at all, like acting in the world in certain ways. There might be cases it might be closer to representation. For instance, let's say, this hyena navigates. I don't know if that's representation or not, but the hyena navigates like 10 kilometers each night to do the foraging, to bring back food and whatever, to feed the whole pack and whatnot. And they're incredibly sophisticated navigators of their environment. They visit places that they visited in the past that had been successful, and they use cues to indicate that it's not a good idea to go to that place again because it's too dry or it rained too much. And so it's very sophisticated integration of cues that determine whether they're going to go in one path or another, or continuing further or returning, because it's a very long process. So in doing that, they're clearly behaviorally capable of very complex navigation skills, right? That's just behavior. They do that and they succeed amazingly well. So we will find, if we poke the brain, we will find aspects of it, right? So let's say we have some little thing that we put on the hyena's head, right? In 20 years, we develop it, and then that can measure almost all neurons in their brain, right? Something like that. We will find a lot of responses
Right.
that
To those.
correlate, that are correlates of that, right? I mean, because it's one side of the coin, right? It's this mind brain behavior, mind brain system. So the brain is not going to be doing something random. It's going to be doing something
Yes.
quite systematic, right?
It will always be, responsive in a very ordered fashion to ordered contexts.
Yeah. It's going to be exactly. It's very closely tied
To the
to
context.
what's
Yeah.
going on, right? So, and all of a sudden, for instance, imagine that there's some challenge because some lion pride is nearby and they either see it or they hear the roars or the smell or whatnot, and they decide to either go back or change their path of foraging for that night. You're going to see that in the brain, right? So does that mean that in the brain they're representing lions and the representation of the lion created?
Right.
I think that that's not a really useful way
No.
of thinking about it.
No.
But we do find these parallels, and by finding these sometimes tight parallels, I think we get into this trap of thinking that the brain has these explicit representations. But
Yeah.
I think it's one of these dangerous words because it just can mean too many things, right? So what do you
It's
mean
not
when you say
It's not parsimonious. And
yeah,
one of the things which we are trained in scientists as good scientists is to have parsimonious terminology. It's one of the prerequisites for reproducible, for a
yeah, yeah,
understandable science generally.
yeah,
So
yeah,
Louis Barrett has a
yeah,
really nice book, if you're aware of. It's called Beyond the Brain. Uh, right? So
yeah,
a, a beautiful book, and she gives an example of face recognition, that honeybees can actually recognize faces to a large extent of human faces. They can differentiate, and they do not have the same structures in the brain the way we have. And in humans, neuroscientists have actually designated certain brain structures as face identifying modules. So now
yeah,
what
yeah.
she argues is that if an organism without those modules can identify face, then maybe it is not about those modules, it's something else, and those modules are just there. Uh, uh, that we find them localized. So maybe we need to think more again in terms of the interactions in not the component that we see.
Yeah, I've been meaning to read that book for a while. I really wanted to read it, and I think that you mentioned in other of your interviews a few times, and
Yeah.
that's definitely a book that I would like to read soon, because I think that so we get into this mode of brain, and then we kind of lack ways of thinking that kind of can free us from it too, right? So it's a little bit
Right.
like sort of like expanding our education to be able to think more freely, more openly.
Right.
And maybe you decide that you don't like it, but at least we have to learn it, right? I mean, I think that's
Right.
the problem. You could say, okay, there's these severe deficiencies, I think, suppose, and therefore I will reject that or whatever. But at least it's an informed version as opposed to not even being exposed to diverse ways,
Exactly.
because you can see that in mental health, right? And illness, people think that it's some dopamine, some serotonin issue
Yeah.
here. So it's like some really simplistic ways of thinking that are incredibly reductionistic. But I think it comes from the lack of being exposed to alternative ways of thinking, literally.
Right.
And I think that the good news is that you keep on seeing more and more coming out that is emphasizing mind and brain, the organism, the autonomy of the organism, and that they don't, that kind of pushes against this naive form of reductionism that, okay, is this hyperactivity in the amygdala that is actually going to explain phobia, and
Right.
and only so, right? I'm not denying that it's
Right.
one
Right. Right. Right.
component
But
of
only so.
complex
And this becomes more apparent when you talk to, for instance, a neurologist. So when you talk to neurologists,
yeah
their perspective, they have much more nuanced view about the brain compared to neuroscientists. And they literally do not believe that brain is actually computing, because they remove tumors every now and then, they remove parts of the brain, and they still see things functioning the same way. They see a redundancy in a lot more different way, and the evolution of brain compared to a lot of neuroscientists sitting in our labs, all day long, or computational modeling all day. So they have much nuanced views as well.
Yeah, that's interesting. Yeah.
So, Professor Lewis, where do you think? So you mentioned principles and laws, at some point in the conversation, that when we are looking at the neutrinos hitting on the Earth or gravity, we are talking about laws and principles. Do you think that there is any possibility of that the central nervous system might work based on some laws or principles? Because I'm asking you because there has been a recent trend towards these unifying ideas. So one of those ideas, which is based in the older idea of forward and internal model, is the whole idea of predictive brain. The brain is a prediction machine, and it just keeps making predictions and matching predictions with the outcomes. And then when you ask, like, what exactly it is predicting, is it predicting the sensory, complete sensory signal, or is it predicting a particular end result? In which space exactly it's predicting? Because between any two space, there's an infinite degrees of freedom, detachment. And then it has gone to an extent that now we have principles like free energy principle, for instance, which tries to explain everything about the brain, like this is what the brain is. So do you feel that there can be principles and laws governing the brain? And is it a good exercise, or neuroscience is mature enough that even if it exists, we will be able to identify them at this point?
Yeah, so I think that I'll go back to one of the things that I mentioned before, which was I feel, while I'm not confident of any one of these paths that you outlined there, I do think that they have quite interesting components and whatnot. But even more broadly, I think that encouraging a subset of neuroscience to seek those principles, either dynamical principles or whatever types of principles, I think is fruitful. I think is fruitful because I think that sometimes we get too much stuck into one mode of doing it, and we find something successful, reinforcement learning, reward prediction errors, and everyone is doing striatum for 2 decades now is being attacked from one standpoint. Like I remember many years ago, more than 10 years ago, I went to a panel evaluating postdoctoral proposals. 8 out of 10 proposals were looking at striatum and dopamine and reward prediction errors. Like everyone the same thing. Some people were doing it really nicely, some people not as nicely and whatnot. But it's like everything was the same thing. So I think that we need a plurality of ideas there, and of approaches, including trying some of these large scale principles. I wouldn't call them laws. I mean, I think that biology is probably something that doesn't have laws in the physics sense, at least in the physics sense, but either laws of biology, or call it whatever they are, or principles. I do think, because like even principles, if you think of, for instance, in terms of dynamical systems or ecological psychology and other kinds of things, in a way, those are the principles, guiding principles.
Yeah, I would call them axioms. I would rather call them axioms.
Axioms, you even would call it axioms. So yeah, so I mean, that's in a way even stronger, right? Because I mean, from which you together, those axioms together with some principles, you kind of expand the way you think about things. So I do think that the search for them is productive. I don't know if it will result in it will end up being productive, but I do think that we can't just continue generating tons of data and inundating the planet with data, right? I mean, just like dumping
I
data.
mean, the amount of data we generate for each experiment now is running in terabytes,
Yeah,
each
I mean, just
experiment, right? Yeah,
dumping the planet in data without some parallel effort to conceptualize them in some law or principle, and maybe it all fails, but also just doing these minute little incremental things that most of us do is also just going to add to pollution on Earth, because it's just like littering the planet
with data houses, yeah,
with
and
yeah with
and
data, yeah.
right, and transferring these data online. I mean, like we really don't count how much energy it takes to transfer data online from one
Yeah,
source to the other.
yeah. So yeah, at one point we will even be counting that and say, well, look, you with this study here, you dump 17 plastic something somewhere,
We'll have
and is
carbon credit for neuroscience.
yeah, is that yeah, exactly. Is that worth it? And so yeah, I don't know. I think
Yeah,
we need both, we need both, and we need to be a little bit more. I think we need to be open to different ways of doing it, and continue being rigorous and skeptical. It's a difficult balance, right? Because if there's something a little new, everyone just hammers it. It's like, oh,
yeah,
this is horrible, horrible, horrible.
right.
But uh, at the
So
same
so
time, just
yeah,
because it's new, it doesn't mean that it's good at all. In fact, the
right.
likelihood is that it's probably bad, because that's on average what we can come up with is bad.
Yeah, not
So
everything new is good.
yeah, so
New,
it has to be
right,
some balance, right? We have to be
right.
it's as if we have to be really rigorous and skeptical, but at the same time open. I don't know if that's possible, if humans can do
So
that,
this brings me to the exact you just touched upon the exact question I was planning to ask you next, which is from a young person's perspective who is starting career in science, and given your experience both as a researcher and as a person working closely with the NIH and as a review panel, uh, what should be the strategy for an individual who wants to do innovative work, something which can lead to paradigm shift, uh, uh, and also wants to work with federal funding, has to wants to have innovation, but at the same time is not willing to compromise too much on being conservative. So how can they navigate the whole landscape of uh, scientific funding and establishing a productive program where you experiment and you try out new things, rather than using every grant to get a new grant? Because I am exposed to labs where everything is about pilot data, because nothing is actually done. It's like by the time you have to collect the pilot data, you're using it for the next grant, right? And then
Mhm.
it becomes a self-fulfilling cycle. There are a lot of labs where publications is a byproduct of grant writing. So,
I see. Oh
right.
wow.
So how do you, like, for a young person, what should be the strategy so that we can be both truthful to the science and the quest of knowledge, and as well as be able to navigate the sociological
Yeah,
constraints
yeah,
surrounding
yeah.
scientific life?
Well,
Yeah,
I would say, this sounds really, how to say it. I mean, there are a privileged few that happen to get positions in universities that have quite substantial startup packages, right? So the US is pretty unique in that respect. That, I mean, if you consider, for instance, I'm at a university, it's a state university, it's a state university, it's
yeah,
limited budget, but and it's a good university, but it's not, it's not the number one university on the planet or whatever that
right,
means. But in any case, so we provide substantial, because the world is competitive, we provide substantial startup packages. So if a young investigator is lucky enough to be in a situation like that, they do have a little bit of a slack, an opportunity there to collect preliminary data that shows that this unusual idea happens to be quite promising, as can be seen from supporting preliminary data. So that's pretty unique, because if you had to if you had to go in without very little data or
right.
no data at
Or no
all,
support. Yeah.
it's going to be impossible, right?
Yeah.
But because you have a few years of support in some universities,
Yeah.
then if you are under that luxury situation, you're very lucky. So that's what I would suggest in those cases, is to pursue your dream and give it a try. And I would gamble a little bit in the sense that you could say, well, you could use your time to do more, to establish your preliminary data in a more conservative kind of undertaking. You could, but and if you're very risk averse, sure, I think that's fine. But I think that there's a little bit of room for
Right.
experimenting at the very beginning of the career, just because of these startup packages.
Yeah.
If you are in a situation where your startup package is much more limited, more modest, and allows you to do a few things and hire a few people in your lab and computers and whatnot, but not to the scope that would allow you to support a proposal with stronger data, then I think I then would suggest that a more pragmatic approach is depressing to say this, right? It's really depressing, but
Yeah.
a more pragmatic approach is important, because then I think you have to switch the game to a much more long-term goal, which is, I am going to try to do these more innovative things, but in an extended period as permitted by funds. So for instance, so you get a grant and you have maybe a small internal grant from the university, and you have an external grant. So maybe you have some extra funds there that you can continue working a little bit on your more original, unusual ideas. So it will require a little bit for you to get those initial funds that you're going to have to be a little bit more conservative, but then hopefully with internal mechanisms at universities, some of which are offered, like preliminary for small seed programs, and so seed grants and things like that, try to gradually build it up. But it's very challenging. I know it's not going to be something, because we don't have, for instance, like in a alternative universe in which you had universities gave you a little bit of funds on a yearly basis for you to just do research.
That does not happen.
Right? That doesn't happen, right? So, but it does happen, for instance. But think of it from this perspective. In Brazil, there's no startup funds.
Oh, so in that case, I mean, US is unique.
Yeah.
We are living in compared to anywhere else I know. The luxury to do anything. I mean, in fact, I have no complaints in that regard. My current position, you are just limited by your for the most part, unless you have a very ambitious project which needs a lot of money. For the most part, you're limited by your imagination in early years. If you, I agree with you. There's a lot of wiggle room compared to any other place.
So I think it's tough. But if you happen to be in an environment in which you don't have that kind of support, which I'm assuming a lot of places is very modest,
right?
Because there are hundreds of universities, and not, maybe the top only 50 or 100 can offer something that is a little bit larger, but there are hundreds of universities out there. So then I think that you have to do more a more pragmatic approach and see if those funds can help you. I'm not encouraging you to apply for something and use the funds for something different, which is not something that's allowed.
But that's what everyone does. Well, because by the time people apply for R1s, I mean, they have done the pilot. It's like they're collecting like 25% more subjects.
I am not going to say that on record, but what I'm going to say is that if you find ways to intersect your interest to the current fundings, let me put it this way, then you can maybe gradually build in that direction too. But it's very difficult, because it will require some preliminary data to convince people that you are on the right track. If your track is, the more unusual your track is, the more preliminary data, right? So if I say things that are, reward and threat work in a completely different way in the brain than people think. Doesn't matter that it comes from me, from anyone else. The only way that this is going to fly is that if you have a ton of data. And so, oh, you know what? I was very skeptical in the beginning reading this grant, but there was so much preliminary data suggesting that when this happens, reward changes the way it's processed. I don't know, whatever, some crazy arbitrary scenario. You can convince people with very strong preliminary data, but that takes resources, right? It takes money to run people. Let's say if you're doing experimental work that runs people, like EEG sessions, fMRI sessions, or whatever sessions that people, it costs money to have the person a research assistant and maybe a graduate student. So not every department is going to be funding a graduate student. They're going to be funded either via teaching assistantship,
or
but for you to relieve them from the teaching assistantship, you're going to have to find some funds. So that's why I think in the beginning you have to be more pragmatic. And I don't like that expression, but like you say, play the game a little more.
Right.
Yeah.
No, that's a wonderful advice, overall, and definitely, one thing, a lot of times when we complain or when we whine about things, we forget that, despite all the drawbacks, I mean, US at least has still, it's still a growing market in terms of still we have more faculty position each year. It's not like a limited pie, as well as there's a lot of wiggle room during your startup, even at.
Yeah, it is pretty unique. It's a
It
pretty
is
unique
unique,
system
right?
once we compare it to other parts of the world.
Right.
I have lots of colleagues across the
Yeah.
world with very different situations.
Right, and that's why it innovates the most as well. I mean, within the limitations we
Probably,
discussed.
yeah, exactly. Yeah.
And also collaborations kind of also give a lot more free room right now, a lot more ability to leverage things, which was not that collaborations. Given that how
collaborations.
online we can collaborate has changed the
Now I
scenario
think
a little bit.
it's a game changer. You can collaborate in ways that
Yeah.
I myself have been incredibly lucky, and I'm collaborating with a great group right from Yale, and we're always online, and every week it's very active, but it's all online.
No, I've seen several of your talks, and my favorite one is the one where I think Professor Pollack from Stanford and Professor Anderson from Canada was there, and and you had separate sessions, and Professor Anderson just dismantled the representational theory of the mind. That has been my favorite, from your series of discussions online.
Yeah. I should watch it again now that you said that there's a dismantling there. I gotta refresh my mind of how to dismantle it.
No, he was very convincing and very precise about it. He had the surgical precision of dealing with the representational theory.
Oh, great! I'll look it up again. Yeah, okay, that sounds great. Yeah.
So, Professor Luiz, one last question before we end the show today is, what is your vision for neuroscience? If you were, let's say, you are like a dictator of a neuroscience republic, the global republic of neuroscience. What are some of the things which you would love to start?
Well, I think that, okay, so I guess I have to say something, right? So I guess so here's what I find. I don't know how to implement it, but I would find a way. I would have we academics do, right? I would create a committee to solve this problem. And the problem that drives me nuts is the following. Okay, I do understand that we all have to be really specialized, because I do research on threat and reward that a very small number of people do and whatnot, and it's fine. But I think that we have to move to a neuroscience that even if you do specialized work, you have to be considerably broader than what we are right now. We're too narrow. It's just unbelievably narrow. I just cannot believe that all the folks that do fMRI barely even know or cite any animal work when they're
Yeah.
doing their papers, and they're not studying language. I mean, they're studying,
Right.
I don't know, something in the amygdala, and they don't even cite any. They cite Ledoux as one, review. That's not enough. I mean, I think neuroscience needs to step back a little bit.
It needs to talk about all the scales. Like it needs to think about evolution. It thinks about development. It needs to think
Yeah,
cross species cognition. Yeah.
that's exactly right. So, not to mention what you just said, like, how are we going to study neuroscience without knowing more about evolution, at least knowing enough about vertebrates? How are we going to do neuroscience without a better understanding of behavior and different schools of thinking and teaching about behavior? So I think we're just too narrow-minded, and that it's become boring, because lots of us got into science because we wondered about too
Yeah.
many things,
Exactly.
and we all love to wonder about too many things, and then it's like, okay, narrow,
Right.
and then it takes the joy out of doing the research. And so,
So I think one of the things you would like to implement is probably flatten the pyramid model in science, because maybe we don't need so many people trained by a single person. We need a lot more young researchers with better salaries, maybe not as a professor, but much livable salaries, and collaborative in a more uh, 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 network space rather than in a pyramidal space.
I would love to, in this republic of neuroscience, I would love to find some ways to have much more collaborative work. It's like, I've been doing research in my lab too much, and why don't we, okay, because we have to all take care of our own careers.
Yeah.
We don't even have time to collaborate. So we barely have time to maintain this one or two whatever grants that support our work.
And the administrative overhead, the number of forms we fill.
Yeah, so
On
I,
every
I think
basis.
that we need to find ways to, it would be great if we could find ways to be much more collaborative in a real sense. Like, I'm participating, not just putting my name in a paper, I'm participating in some
Yeah.
project.
Like actual
And
collaboration. Yeah.
yeah, and I just like, we just, it's just like too individual based, right? And I think it would be a lot more fun for everybody if we found a system that recognized and valued that. But I don't know if it's possible, but since I own this republic, that's what I would do.
No, we try to create these spaces within our own capacity. I mean, that's why we are talking here, because you have created a space online. That's where I encountered you. And so within our capacity, we are trying to do that.
Yeah.
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 But those republics are virtual for the most part right now, and small.
Yeah. Yeah, that's right. Yeah, that's right.
So, Professor Luiz, it was great speaking to you. And for the viewers, I would like to remind them that you are one of the most humble professors I know, in the sense that, at least in neuroscience, I don't know many people who are very humbly critical of neuroscience in general. And your book is really eye-opening, and it has the same kind of feeling, which is very apparent, while talking to you. The kind of
All right.
satisfaction you have, as well as the vision you have, and the openness with which you talk about things, is also very appreciative.
Thank you so much. Thank you so much. It's very kind. Yeah, great to hear.
Thank you, Dr.
Okay.
Luiz. Have a great rest of the day.
Yeah, bye. Bye.